UVA Darden.
Good Disruption, a lively discussion between UVA Darden School of Business professors Yael Grushka-Cocaine and Mike Lennox on cutting-edge technologies and practices that are challenging the status quo.
Hello, Yael.
Hey, Mike. How are you?
How are you doing today?
I am fantastic.
All right, I'm going to begin with a question, as I
Okay.
often like to do for you. A history question for
Okay.
you.
Yes.
What was your first computer? What was the first computer that you owned?
Ooh,
Or
myself.
computing device?
Yes, at the household. Can I go back to my
Oh,
childhood?
yeah. No, that's what I was
So
expecting.
my dad was always ahead of his time. I definitely remember our Commodores. What was it? 3264, those kinds.
Oh, yeah.
Those were
What year
probably,
would that have been?
I don't know, 80s?
80s?
Mid-80s.
Okay.
Yeah.
So I always say my first personal computer was an Apple IIe
Ooh.
that my parents got me in high school.
I
So
never
now-
had Apple. I was never a Mac or Apple person.
Well, for those listeners who are maybe a little younger than us, this was before the Mac had even been introduced. So this was literally one of the first personal computers.
Yeah.
But even before that, my cousin had gotten the Atari system.
Oh, we had that. That we had it.
You had that?
Yes.
I didn't have that.
Yeah, we didn't
I
have
was deprived as a
My
youth of
dad-
gaming systems.
My dad was a really big
Yeah.
computer geek. He loved that stuff, even though he was a chemist, but he used to buy a lot of equipment very quickly when it first came out.
Yeah, well, I mention this because if you think about back to those heady days of like the 1970s and 80s when these first personal computing devices were coming out, in many ways, here we are, many years later, nearly 50 years later, and the underlying technology is more or less the same. You
Yeah.
take a bunch of silicon and you have your silicon-based computers here with a whole bunch of bits with the 0-1 binary decisions that are being made. And we've scaled it to incredible heights. But the fundamental core, physics, if you will, have been the same. And now we've got something called quantum computing.
Well, it's been around for a while.
Well,
but
that's true. That's
or
true.
at least I've been hearing the term
Yeah.
quantum computing for a while, but I think there's more and more excitement and investment that makes it feel like it's coming close.
Well, of course, it's not real until we cover it on this podcast.
Right.
So this is its moment.
Announcing.
We are announcing this thing called quantum computing.
Okay.
Clearly, no one else has talked about this, but we feel like it's time. It's time. I think we've been maybe fearing this topic because this is a tough one. This is a tough one to get behind the science. My basic limited understanding here is, again, with our traditional silicon technology, 0-1 binary systems, we now, in a quantum world, have the ability to have bits that we call qubits that have multiple states that they can take, not just 0-1 binary. So, for example, if it could take 8 different states at any one time, and now you multiply the number of these that you have, you are multiplying exponentially in essence. And so these computers have the promise of being much, much more powerful than anything we've seen to date.
Okay, so that's super helpful. So let me kind of maybe rephrase your insight or kind of cast it in a different way to think about it for those folks who don't really even understand the silicon bit part of the things,
Yeah.
let alone the qubit part of thing. So the fact that we're using certain ways to kind of store and capture the data, what does that affect? That affects how fast we can process things and actually compute, let's say, run through processes or run through queries.
That's my understanding. Like
Yeah,
at the heart of this is kind of
the speed.
computational processing here.
Okay.
This is Moore's law, right? Processing power that we could get out of one of these machines.
Okay. And so then somebody might ask us the question, well, those computers that you talked about that we had back in the 80s in the good old days at home, the size has changed. Like we know that there have been advancements
right.
and there has been kind of evolved, the technology has evolved. We all know that we're walking around on our phones with the computing power of, several of these old-fashioned PCs. So what have we seen so far that has happened, and how is quantum computing going to be different?
Yeah. Well, so I think, at one level, this is not a new concept. So going back to like the 1980s, people had proposed the idea of a quantum computing using these quantum properties at the very micro level here for this purpose. The first commercial quantum computer was introduced in 2011 by D-Wave Systems. So This has entered the marketplace. Now, clearly, it has not penetrated it at a high level, but every day it seems like there are now announcements, IBM, others that are kind of making more advances. And the way I think about this from a kind of a technology race, if you will,
Yep.
if you take again, an 8-bit computer in the traditional silicon versus an 8-qubit quantum computer, the 8-qubit quantum computer is, exponentially more powerful. Where we are today is we can now build chips that have, I don't know where we're at in terms of trillions of different processors in there.
Right.
We're not there with the qubits.
Okay.
But the race is this one that's more powerful as it improves and becomes more economical in particular. There are points at which you could believe like this is going to overtake the computational power of the machines we have today.
Fantastic. So that helps us understand there's going to be a limit to how much we can get out of the current way that we compute and out of the current ways that we build all those CPUs, whether they're in our home computers or at our devices. There's going to be a limit. We've gone smaller, we've gone more powerful, but at some point, whatever this innovation is, because of these multiple states that each one bit can take, and because of the different states in which and the data that we can capture there and the speed in which we can process it, it's going to quickly overtake it and be able to perform functions that we were not able to perform.
And I think what's going to be interesting as this plays out is you're going to see it pick off niche applications first, right? So you're not going to use a quantum computer to do, let's say, like the basic calculations in math that a calculator could do, because again, the current technology does this incredibly well. The ones that I've seen people mention that are kind of like maybe the first that will start to see the use of these computers, cryptology.
Okay.
And in general, something both of us are interested in, like highly complex problems, these what we call technical like NP hard problems. So I've seen like the traveling salesperson problem, which Yael knows very well. But for those of you who've never heard of this is just very simply, how do you design the optimal route for a salesperson visiting a number of different, homes, let's say, if it's a delivery person on Amazon. And it's at one level a fairly simple to describe problem and everyone understands it, but it explodes computationally as you add more nodes. As the number of places you're visiting increases here. So
I have another example of an NP hard problem, which is from my field. How do you plan a project at the minimum duration when you have limited resources? It's actually really hard to solve.
Yeah. So I think those types of problems will be the first ones we'll apply quantum computing for. And then again, if it continues to get more powerful and less costly, you could see it completely overtaking traditional computing.
So quantum, just the name quantum, like when I hear quantum computing, quantum mechanics, again, we date ourselves, but, quantum leap comes to mind, time traveling and the metaverse. So far we've talked about computational speed and capabilities, but where does the whole time space continuum kind of come to play? Is that a part of this equation or not?
Okay, this is where we're going to start losing our track here.
Now a good time to bring it next.
Well, let's wait 1 second, because I do think some things that I think we do understand that we can bring to the discussion, which is to be able to work at the quantum level, at this literally subatomic level here.
Yep.
You need a computer that has some protections, if you will, that we don't have with our current kind of silicon-based computing. So one, sensitivity to noise. Ooh. So it needs to be a quiet environment. Sensitivity.
Okay, most of our computers are not in quiet environments.
That's right. Sensitivity to movements of any type, like just even a micro little movements in like an earthquake, of course, but something smaller, that's going to cause problems. So you really need to have these very, very protected. And my understanding is that's one of the big challenges of making these systems, first of all, operational, and second, economical.
And so what are some examples of places where we might find some of these quantum capabilities? Yeah.
Well, again, I think some of these bigger companies like IBM and others are trying to build these systems. I think about, as we always tend to reference in this podcast, like pop culture references.
Yes.
So there was a great Netflix series called Devs.
Yes.
I don't know if you watched that
one.
I
have not.
And the heart of it was them building this uber sophisticated quantum computer. And they do a really nice job visualizing how this would work, where it is like a room in a building built distinct from everywhere else. And then the computer itself, I think using magnets, was like levitated to protect it from variations. And it was a, clean room, but also, sensitive to noise and all of that. It was handled there. So I think that's where at least the belief is these systems might need to have some of that.
Interesting. We're going back to the good old days of a computer room and a big server room that we all have to go to conduct our functions.
Now, what I'm curious about is that what the vision is for a commercially viable system? Because that seems like that's pretty expensive to build one of these,
and limiting,
and limiting into what you could do there.
Yeah.
And so I think that's as often it is with technology. Like, how do we push down the cost curve to make these things viable, even if we've proven theoretically of how these will work?
And so that will be really important when we think about this as a disruption. It's like, is it about to happen? Is this near term, or are we talking about the next 10 years? And who exactly are we disrupting? Okay, now I'm going to bring in
we've done it. We've gone to the limits of our knowledge on this topic to the extent we even had any. So
well, I'm so excited and honored to bring in not only professional acquaintance but a friend. Joab Rosenberg is here to join us today. He is the founder of many different startups, but in this case, general partner and founder of QBeat. QBeat Ventures, a venture capital fund that specializes actually in these early stage investments in quantum technologies. So just the right person to help us. QBeat is the first fund in Israel dedicated to quantum technologies and one of a few globally so far. I suspect that will change very quickly and there will be a lot more activity globally. QBeat is a fund launched earlier this year, so it's pretty new. It has it's raising $100 million to invest in 12 to 15 early stage hardware and software startups in the quantum field, from pre-seed to Series A rounds. Joab, welcome to our podcast.
Thank you very much. Thanks for having me.
Well, tell us all the things that we got wrong when you walk down the street and people ask you, what is this quantum computing? What is your elevator pitch?
No, I think you are quite right. By the way, my first computer, I had a Commodore 64 and an Atari. But to be honest, when I was, I think, 13, I still punched cards for an IBM mainframe in Bar Ilan University. So I've done that too.
You're clearly more precocious than me if you were at the university at 13. So that's...
No, it was kind of thing for these early high school students. It was fun. I think the quantum computers will look a little bit like that, like, as you said, a computer room. But most of them at the moment are connected to the cloud. There was no cloud back then. So today you can use them over the cloud. If you go over to Amazon Braket, for example, or for IBM quantum computing, you are already able to play with computers and pay money. So IBM already revealed that they had a cumulative over $1 billion in revenue from the computers that are putting on the cloud in the last decade. And the other companies, even the private ones who are building computers, Quantinuum, for example, they have a revenue of about 50 million ARR. So this is quite big. And I think there's a big misconception that people don't realize. People usually imagine it's something that will happen in a decade from now. And up till then, it's an open field. But there are companies already making revenue.
Can I ask you a question on that? Is the future then of this not that, we all go out and buy our quantum computer to have at our desktop here, and rather, like you said, large players building out basically their own data centers, if you will, connected to the cloud, providing services. So again, we won't be buying our own quantum computers per se.
Yeah, I think not in the near future anyway. There are enterprises and corporates that are buying on-prem computers from private and from public companies. So you will see that. And in that sense, it's quite similar to the mainframes of the 60s, 70s, and so on. Each of them, if you buy on-prem, would be between 20 to 40 million each.
Wow.
These are the prices. I think IBM already built more than 75, I think they said. So it's quite advanced in terms of Commodore 64, right? So they're still small. They're not doing the things that we know to prove they will do when we scale them up. But people are buying it mainly to try and get ready, because it's not something, as you said, the knowledge gap is quite huge. You need to train people. The talent gap is quite big. So if you want to be ready, and of course, the main question that we will have to address is the timeline. But if you want to be ready as a corporate now, as a user, you need to start building your own quantum computing team internally. So either you use it on the cloud or you buy your own, depending, on your secrecy, on your priorities, because all of the queues at the moment of all the different computers that are available are all taken, and you pay something about like $1,000 to $5,000 per hour to use the computer over the cloud. So some companies may rather quickly get to the point that they say, we want to have one on our premises.
Amazing. And can you give us an example of, let's say, what kind of task would a company go to the Amazon, quantum computer and try and conduct? Like what from your experience and from your knowledge, what kind of tasks are people engaged in, right? Like obviously, is it the traveling salesman, or is it something kind of totally different that we haven't even thought of yet?
Yeah, I think it's the hard problems you mentioned earlier. You can put them into families of problems. In terms of industries, it's quite rich. So it starts with the financial world, any material sciences, chemistry, drug discovery, mobility, logistics, cryptography, many problems. In terms of the family of problems, it's what we know to be the difficult problems of computation. Similar to simulating molecules, like big molecules, especially when you don't have a lot of data. So AlphaFold is not relevant. You want to design a very new one. Material sciences, fertilizers, batteries. Up till now, we have to say, because of this kind of a mistake that we've done in the 1940s, inventing the 0-1 kind of computer, whenever we want to do simulations of molecules, we do approximations. Because, the degrees of freedom of a molecule, a big molecule, many atoms, they can move in space. It's impossible to do on a regular computer, high power computer, or anything else. So we're doing approximations. And therefore, for example, when you do drug discovery, then you have a decade of experiments to make sure you're not killing the person. So it takes you $1 billion to introduce a new drug. But if you're able to really solve the physical problem of how the molecule will fold exactly with a quantum computer in the future, you save years and years of introducing new drugs. The same goes for climate. We're not able to do climate calculations on computers as we know them today, but we will be able to do much more on computers, quantum computers. So in terms of climate solution, trying to put you in the disposition to say it's a good disruption, you will be able to do that. But it's really a plethora of different algorithms in many different. If you go again to the IBM website, you'll see endless amount of use cases that people are already playing with, in the sense of taking a small model, translating it from the classical computer to the quantum software language, which is not an easy task, and then running it on the small computers that we have available at the moment that usually run around 200 qubits. But again, for the pedestrian listener, when we say that the quantum computer, let's say, grew from the scale of 100 qubits to 200 qubits, it's not 2 times better. People have to have in their mind 2 to the 100 going to the 2 to the 200. This is huge numbers. The improvement is unbelievable.
I saw one stat that said that the Google's Sycamore system took a problem that took over 10,000 years to solve by supercomputers and got it down to 200 seconds.
Wow.
Yeah, that's the kind of number Google like to put on the PR. Now, on the Willow, they've done even better. They said septillion years, which is like many times more than the age of the universe, that they could do on the Willow in 2 hours or so. I don't remember, or even less. But these are problems that are not that practical. So there's a differentiation, again, between different levels. There are the mathematical abstract proof that we do on complexity and so on. So the Shor algorithm is the best example, where we know that we could, for example, break the RSA code which was based on problems that regular computers, could not do. So we know as a proof that we could do that when we scale the computer enough, but that will take longer. Then there are the practical, actual problems that we want to solve, like the traveling salesperson. And then we can say exactly like how much qubits we will need for which kind of problem. And then I think the most interesting at the moment is like the tinkering. So as usually happen with algorithms, you have these software developers or PhDs in algorithms that come up with a new solution, a new way to do that. And at the moment in quantum computers, it's a very new realm. So people can come up with new ideas that are more on the tinkering side, not this septillion compared to 2 hours, but actually I can save you like 40% of the time on option pricing, or I can save you 40% of the people that you are now doing in your huge data center and make it much simpler and cheaper. So these are the kind of things that I think will come earlier and will be more surprising and may catch many in the industry unprepared if they don't start to use it now. So there are examples of companies, enterprises that are doing a lot, like JP Morgan, BMW, Aramco from Saudi Arabia just purchased a computer. And there are others that are lagging behind, and I think not understanding how quickly it may change the industry.
I'm curious. Oh, sorry. I was just going to ask the programming side. I'm just a quick deep dive on that. So I am old enough to remember like machine language, right? And like that going back to the real basics. And then we of course built a whole infrastructure off of like that base level programming. So now we can, like average human can do this here. You don't have to be that steeped in at that level. Is a similar thing happening with quantum computing, or are we at a point like we're in the machine programming level of
the basic of quantum computing?
Yeah, right? Yeah.
Well, we are reinventing the whole stack from the hardware to the top level of the software and application layer. But you see quite a similar phenomena. So you don't need to really know the assembly of it. You don't need to know how to control the actual qubits, the physical qubits, because there are many different types of qubits. And then you want to shield it even further, for people who are from the drug discovery industry or from the financial world. And you want to let them have this like upper level kind of language that allows them to, just translate the regular problems into quantum problems. But in any case, there's a big Israeli company called Classic who would build software for quantum computers. I personally believe that you will not be able to really shield it completely away, and someone who doesn't know what a quantum computer is will just run his software over and above it, because the principles of it, the fact that you get a huge advantage, an exponential advantage, you need to understand what superposition is, what a qubit is, what entanglement is. Otherwise, you will not be able to take the advantage that you can. But it will still be in an upper level, and maybe AI will help you, as a co-pilot of some sorts.
Yeah, that's super helpful. So many questions. So fascinating. So it really helped, I think, bring to life your comment around the, let's say, the pharmaceutical industry as a practical application in terms of like thinking about the disruption side of things. So I just want to kind of reiterate and thank you for that example, because quantum computing is allowing us to do more exact calculations, because we don't need to approximate as much, because we can process to a much finer degree. And it's even like a mind change around the fact that there are drugs out there that are suitable to solve certain, health situations, that our only limitation right now in discovering them has been our ability to exactly define them and study them in that specificity. So we've had to experiment with human people for like decades, right? Like it just blows my mind that that's actually something that we can change, right? Well, we can get better at it.
And this is, a question for you, Joab, that I'm kind of interested in is, I think about something like chess, right?
Yes.
And so we've had these great advancements in AI.
Right.
But to be clear, what AI is doing is it's approximating a solution to the chess game in ways that are far more sophisticated than we as humans can do. But if I understand correctly, quantum might let us actually solve chess, like actually calculate the optimal path at any point in time in the game. First of all, is that characterization correct? And if so, what does this mean for AI if we're no longer using the techniques of AI to approximate solutions? We're actually just literally solving problems that are out there.
Yeah.
I do believe chess is quite a small problem comparable.
Right.
No, so chess, I think computers today can actually solve in the sense of going through different possibilities and putting different weights on different possibilities. And therefore, you're right to say that they're solving it in a very different way than, a world champion human being who's playing chess. Because he cannot do this calculation. But let's remember, computers have a better memory than humans since the 1940s. So they're getting better and better, but they always used to have capacities that are better than human beings. Just calculating 1,206 times, I don't know what. So I think, but it's completely true that some of the end users, the potential end users, don't even have in their mind the possibility of using such a computer. Because let's say, Yael is right to say, sometimes it's about computing in a more exact way, but sometimes, like in the traveling salesperson, it's about taking many more constraints and many more parameters, more than you ever thought and more than you ever thought that you need. Because when taught in the university computer science, they told you this is unsolvable, so don't go there. So all of the practicality was about how can we do things in this area and not in that area, because it was completely impossible. So people need to learn again what are the possibilities. And I think many of the new algorithms must come from there when people realize what's happening. And of course, as computers scale, that's part of the thing that we still need to see coming.
Yeah, and related to the scale, Mike mentioned this sensitivity to sound, this sensitivity to movement, this fact that you kind of reminded us to think about it more like an old traditional kind of mainframe. So is there a lot of kind of activity that we're seeing trying to change that, trying to make these quantum computers more robust and more accessible?
Yeah, that's the main effort. I think the two main problems of quantum computing are, one is scaling and protecting against noise. And the second is the talent gap. How do you get people? Because it's much, much more difficult than AI or blockchain or any other revolution that we've seen to teach quantum mechanics. That's a different story. I think that in terms of scaling, the competition is still open. It's unlike the transistors. All of the computers are built out of transistors from all models, from all companies for the last, 60 years or so. In quantum computing, we still have different modalities for the physical qubits. So the hardware is very different. We have at least, let's say, 5 leading modalities, and there are some more that are more secondary to them. So IBM, Google, and the others are doing what is called superconducting qubit. So it's based on superconductivity, and therefore it needs to be in a fridge and cool down to millikelvin. And that limits the scale of how you can take it up from 200 qubits to 20,000 qubits. Then there is neutral atoms. That's like the latest technology. It came out of Harvard and MIT and really accelerated fast. So they also have about 1,000 qubits by now. QEra is one of the companies that Google just invested in together with software. It was 230 million round. Then there is trapped ions like Quantinium that is about to IPO hopefully this year. They raised from JP Morgan in 2024 300 million at a valuation of 6 billion, and doing a roadshow of over 10 billion. And then there's the photonics, the ability to build computers and qubits out of photons, the particles of light. And the most famous company there is PsiQuantum. One of the founders is the grandchild of Schrödinger. And they raised 1.3 billion and still raising the valuation of, again, over 7 billion. And they're building a huge facility both in Chicago and in Australia that will be the computer. So there it's not even a computer room. It's a computer, football field or 3 football, that big.
That strikes me, putting on my kind of competitive strategy hat, that like it sounds like we're still in the period of before the dominant design has emerged,
Yes.
which is always an interesting time.
The
kind of
VHS, Betamax.
yeah, right. This period where there's multiple approaches, not always guaranteed that one will win, but likely there'll be some winners and losers then on the underlying architecture here.
Yeah.
And the trade-offs are usually about how do you prevent noise. That's the big game. So you need to prevent it on the physical level in terms of whether using atoms or photons or Josephson junctions of superconducting qubits. And then there's a layer of error correction like you have in classical computers. But the error correction on quantum is much, much more difficult, to the point that people thought, I think at least until 20 years ago, that it will not even be possible. And for that, you need to go deeper into what quantum mechanics is and how strange it is. Because when you measure it, as you know, you change the system. So how can you find out if you have a correction? Because if you want to check if you have a mistake, you're already measuring it. So you're doing something to the system. So it seems logically impossible. And then some very clever people managed to prove that there is a way to do error correction. That's part of what Google actually demonstrated last December. That was like, there was a big PR, is usually from the West Coast. So it was nice on the one hand, the septillion years to compare. But the real thing that they proved is about error correction and the ability to actually implement it.
You mentioned before, and we purposely avoided entanglement.
Yes, I had it on my
list. So can you just explain for our listeners here what that basically means from the quantum world, but then how is that relevant to the quantum computing application?
I did both physics and philosophy of physics, so I'll try not to go too much into the philosophy of it. When I graduated in 1990 or so, and I said I'm interested in entanglement, the physicist told me this is not physics, let alone technology. This is philosophy. Go and study philosophy. And 30 years later, I'm in a lab in the Weizmann Institute, or you could do that on your laptop and you actually play with entangled pairs. That's quite astonishing to me. So there are maybe two or three basic principles of quantum mechanics that people should understand about the qubit. First is superposition. That's the ability of an atom or a photon to be in two states together, similar to the Schrödinger cat, that can be both alive and dead. And again, the main thing to understand, it's not that we do not know whether the cat is live or dead because we didn't open the box. We know as physicists, we have a proof, I cannot do it here, that the cat is actually both alive and dead. So the atom is actually both in the state of 0 and 1 at the same time, which allows you to compute kind of in parallel many, many different possibilities. Like if you have, let's say, 3 regular bits, you have 8 options, right, of 0 and 1, but you need to choose one. You either choose 0, 1, 1 or 0, 0, 0. You need to put the electricity and the current to go through the transistor. With a qubit, you can choose to calculate on both 0, 1, 1 and 1, 0, 0 and 1, 1, 1, and it will compute all of them together. So that's superposition. And that has to do with a single qubit. Entanglement is a completely different phenomena that Einstein and Schrödinger came up with in 1935. That is actually has to do with two quantum particles, and that allows you to fully correlate the two particles. So if you know you have one result at one, you can immediately know what would be the result with the other. Again, it's different than the classical phenomena of correlation, because in classical phenomena, if you, let's say, mix 2 coins, what do you say in America, a dime and a cent, you take your hands away and you don't see what you took, and you find out one of them was a cent, then you immediately know the other one was a dime. That's not the correlation of entanglement. Entanglement is much more weird than that. And the fact is that they're both in superposition, and only when you open one, the other one falls back into the other option. So it's kind of a mix, like a qubit, what I said about superposition. And only when you open one, the other one, which can be at the end of the universe, will collapse into the other option. And that's what Einstein called spooky action at a distance. And that's to be honest, a phenomenon that we as physicists still do not fully understand.
And I've heard this argument that you could have like two, I guess, computing systems that are physically separate, but in communication in that way. Is that the idea here?
Yeah, that's why you sometimes hear also about the protocol in quantum computing called teleportation. It's not really the beam me up, Scotty thing. It's not this thing, but it's based on the entanglement and the weird phenomena of entanglement. By the way, it's a very interesting historical story because there's a book called How Hippies Saved Physics. And it's about physicists in the 1960s, 70s who were hippies, mostly Berkeley on the west side, but also others. They were very interested in entanglement. It started around 1964. And they tried to really do physics experiments on telepathy and all these kind of things, seances and things. They didn't succeed. But out of that effort and out of that computations and theory came out the quantum computer.
I love
Wow,
it.
that's fascinating.
Now I'm going to say, wait a minute, all of this innovation, it's not because of, improved capabilities around computers and processing and how we think about all of that. It's just because now, marijuana is legalized in a lot of more ways.
A lot of creativity flowing out of the world.
This is excellent. Like, I think, and now finally I understand where the whole Doctor Strange comes into play with the whole teleportation. So this was very, very helpful. We've learned a lot, and I can already see all the exciting activities that you're engaged in as a VC in this field, and kind of both advancing it from the instruction and the academic side, but also from the business side. So thank you so much. Are we ready to make a call?
I think so. I mean, I would observe, we haven't talked in great detail about like the consequences of this.
Right. The disruption, so to speak.
The disruption.
Right.
And we can think about it, obviously, as we sometimes do from an economic and business standpoint. And I think that's fascinating in itself. But
and
then
the application that Joab mentioned, all the various applications, just my mind is blown in all the different ways in which this could disrupt various domains.
Yes. So I'm going to go back to the pop culture reference, which I think is very fanciful. But the Dev show,
Yes.
at the heart of it, they use this quantum computer to basically make predictions that are accurate, in the sense they will tell you exactly how the future will unfold. This is your crystal ball, right? So these aren't just approximations. Like, it is incredibly accurate, and they can only predict like 10 minutes into the future, but then they're able to like get further and further further out. And you can imagine the implications of that if we know exactly how individual humans and others would behave. Brings up huge questions about free will versus determinism.
Back to the Future and Minority Report are all coming to mind.
Yeah, and so I'm going to assume that is the stuff of sci-fi. But let's say we do get better at some of these things, solving some of these complex problems, forecasts that are more accurate and the like. Is there a downside to that?
Well, there's a lot of disruption, I'll say. So like, aside from the obvious, like, companies are going to change, people are going to lose their jobs because there's going to be evolution, which always happens with big kind of step changes. So those could be downsides for sure from a societal perspective. The benefits of such a technology could be mind-boggling. All the risk analysis that we do and all the decision-making under uncertainty.
The healthcare examples we were saying, like, could we solve major, problems and illness and
a whole new reality? I mean, talk about promise, right?
Yeah.
We could cure one of those diseases in some way, or learn how to predict better who's going to get ill and how to treat them.
I've got a new future topic for us, by the way, because we did this in my student seminar recently, but the curing of aging, which is something that people are really working towards and have said that quantum computing, that's true. That's right. If you could stop my aging, I'd be really happy. But again, this idea of like, could we move to a world of like solving disease and some of these fundamental problems? Obviously, really, really intriguing. From maybe an economic, but could relate to societal, it is interesting, this notion that, again, we might not have a quantum computer in our pocket, but we do with computing. If it is a handful of companies or entities controlling, these large, powerful computers, that starts to raise some of these questions, either about market concentration or just even political power that could agglomerate to those companies. But I'm not sure it's any different than things we've talked about before with AI and big tech and the like as well.
So definitely a disruption and a good one. Is that our call here today?
We have our bias in this podcast. It is called good disruption. I think we're grasping at straws. I think this is a powerful technology that has a lot of promise. So I'm going to go, and I think is a disruption. Like it might take a while. Sounds like we're still early stages from a market penetration standpoint. But I'm going to go with good disruption.
Okay.
How about you?
Good near future disruption. Not quite here yet, but probably not that far either.
Well, we don't know, right? I mean, this is, again, I joke with my students that if I could forecast technology, I'd be living on an island that I own somewhere in the Caribbean.
Would I be teaching it?
I probably still would be. I do love it. I do love it. But, and I think this is a technology that's been discussed for a while. It does seem to be on this improvement. As we heard, lots of investment, lots of revenue being produced. So like, this is real. This is not like a technology that was fanciful at this point. How fast that diffusion curve moves, how fast that improvement curves, all open questions here.
And I would call the attention of our listeners that I definitely heard Joab talk about like a real talent gap and a knowledge gap. So it's on us to go and kind of try and challenge ourselves to learn something really, really complicated.
Quantum coder.
Yes,
everybody should be studying to be a quantum coder there, it sounds like.
It's nice to know that there is sophistication out there, that Gen AI won't just dumb everything down, but actually we are going to have to rise to the occasion and learn something new and challenging.
Now, before we end, I want to make sure, because I said good disruption.
I'm saying good disruption.
Okay, that's what I thought. I just want to verify for the record. Yeah, you can't avoid the discussion there.
It's good disruption.
Yeah.
And I would invest in Joab anytime. So, yes.
Excellent.
He gets my vote.
Well, we were scared about this topic. It's a tough one, but
People have learned.
We've learned. And that's really what this podcast is all about, is whether we learn.
Thank you so much to our guest. And thank you, Mike, for this topic.
Yeah. And thank you, as always, to our producer, Gary, and to our lead researcher, Becky. We would not be able to have what even seems like an intelligent conversation, maybe to some, without their help. So thank you.
Thank you.
Good Disruption is a podcast from the University of Virginia Darden School of Business.
Darden.